Lab Report 2, Motion of a Falling Object. In this lab, we observe the motion of a falling object and the forces involved. In this case, the object is a ball formed from two crumpled sheets of paper. In evaluating the motion of this ball, we understand the effect an unequal force has on the position and velocity of an object. The main concepts we will be focusing on are Newton's first law, which states that an object at rest stays at rest and an object in motion stays in motion at a constant velocity unless acted on by an unbalanced or outside force, and Newton's second law, which is the momentum principle. Specifically, we are going to analyze the models of the different velocities and positions by evaluating the object with different forces involved. The computational models will include forces such as drag force and force of gravity to create a predictive model. As you can see in the video to the left, a ball of mass 0.009 kilograms is dropped in the negative y direction at a height of around 7 feet. Through trial and error, I came to the conclusion of using a crumpled up paper ball because it was the perfect object to plot the changes due to the drag force and the force of gravity. After inputting the video into Tracker, I was able to plot the points and intervals at which the ball was positioned. This created a table for me to create my observed position versus time graph. In my observed position versus time graph, it is clear that the ball moved in the negative y direction with a velocity that was not constant throughout the falling motion. Next, I modeled the position versus time graph of the same ball if gravity were to be considered the only force in the experiment. This means that the net force is equal to only the force of gravity in the y direction. Therefore, in my code, I altered the net force in the y direction to be equal to the mass of the ball times the negative gravity. In the next modeled position versus time graph, I consider the drag force as well as the force of gravity. Drag force is defined as a force acting opposite to the relative motion of an object with respect to a surrounding medium, which in this case would be air. With the drag force pointing up and the gravity force pointing down, this would create a different plot than the position graph that considers gravity. In this model, the net force is equal to the drag force plus the negative direction of the force of gravity. Because this graph is considered to be the most accurate computational model of the observed motion, I had to incorporate the drag force equation into the code. However, while calculating the drag force, I realized that I would have to estimate the drag coefficient b in order to be as close as I could to the graph of the observed motion. When comparing all three graphs, it is clear that the position in the graph created by incorporating gravity as the only force is greater in the negative y direction than the two other graphs. Conceptually, this is because we did not account for the drag force that would be working opposite to gravity, explaining why it seems as though the model falls faster. Moreover, when creating the graph incorporating both gravity and drag force, I had to estimate a drag coefficient that would project a similar model to the observed motion. Following the momentum principle, I was able to find a trend in the drag coefficient, creating a graph as similar as I could to the observed motion. However, it could not be exactly the same, as there are a few experimental assumptions and errors that could have possibly been made. If we were to examine the terminal velocity of both models, we would be able to see that the model that includes both gravity and drag force would curve down to terminal velocity. This can be seen at where it levels off in the graph. Terminal velocity is defined in this lab as the velocity reached when the force of gravity is equivalent to the drag force. In terms of the momentum principle, this is when the change in momentum, or net force, is zero, meaning there is a constant velocity. If the ball was dropped with an initial velocity, the balls would reach the same terminal velocity. The only way that the terminal velocity would change is if the initial velocity were to be greater than the terminal velocity. For each of the models shown on the screen, I have altered the code to have an initial velocity of -1 meters per second in the y direction. Similar to the graphs for terminal velocity, it can be seen that despite the initial velocity, it reaches the same terminal velocity. Throughout this lab, there were a few points at which assumptions were made in order to analyze results. A few assumptions that we would have to make are that the initial velocity of the ball is zero for computational models, the drag coefficient is fairly accurate to match the observed model, and that the only forces in this experiment are drag force and the force of gravity. Moreover, in comparing the model that incorporates drag force and gravity to the observed model, some errors that may have caused the slight difference in curves include the angle of the camera that shows a slightly different position and the hand-chosen plots of the position in each possibly blurry frame. Despite these assumptions and possible errors, this lab was a fairly precise description of the momentum principle and the ways in which forces affect dependent values such as position and velocity.